I'm Hirotaka Yoshida. The title of my talk is the overview of SC27 WG2 and lightweight cryptography. This is joint work with Takeshi Chikazawa, Working Group 2 convener from IPA. Okay, this is a table of contents of my talk. The first part is the overview of the SC27 Working Group 2, and I will give some introduction, and then I will talk about the ongoing project and for future perspectives. I will conclude for the first part. And then the second part, I will give a presentation, the overview of a lightweight crypto, and the background design and application of lightweight cryptography. I will explain about my own cryptographic design called the NIST LWC. And I will explain about the collaboration work of ISO SC27 WG2 with ITUT SC17. And I will conclude the second part of my talk. Okay, this is introduction. I give you some brief introduction to SC27 Working Group 2. What is the mission of the SC27? If you try to develop and maintain IT systems or devices, and you want to provide various services with the users by using internet. Examples of internet banking are many years already, and the connected car services nowadays. However, if the attacker compromise your system, this will be a huge problem, financial loss of trust, etc. Therefore, your information should compromise. If the attackers compromise your system, this will be the huge problem. So therefore, your information you should provide a fundamental framework and methodology to ensure the security of your system security. What is the goal of the security? It's mainly CIA, and how we try to achieve these goals. The top layer is the goal, and the second layer is the sub-goal. To achieve this sub-goal, we provide technical means by means of cryptography. This is what our mission is. So the next slide is management and collaboration with respect to SC27 Working Group 2. There have been a great amount of work to develop the standard in Working Group 2. For this, we definitely excellent leaders. Who are they? The first leader is Luis, followed by Malaika, Kenji, and the current ones, Takeshi Chikazawa and Toshio Tatsuta, and the currently Takeshi Chikazawa again, and myself, Hirotaka Yoshida, as a company support. Collaboration and with the partners, we Working Group 2 are not alone. We have many good friends to work together. There's essential reasons for this. We develop standards for generic purpose, but we do not develop standards for specific applications or specific industry. But our friends, SC31 or TC68, they do. Currently, we have lots of good friends across the globe. ITUT, MasterCards, HC, Global Platform, CSA, ISC, Structrust, IEEE EU, H2 2020 project. We exchange letters as a friends, so-called liaison statements. And there are some consideration and discussion points in Working Group 2. We are really based on our project or standardization technology is really heavily based on mathematics. What did the mathematics do? The mathematics or cryptography, we use this. We can reduce the problem rather than solve the one. We can't really solve the problem, but we can reduce the problem to have keep the key securely. And we really closely take a look at recent results from cryptographic community like ISCR, security analysis and performance analysis. The daily base researchers really watch at what the results are, and we can reflect their results to this standardization project or work. And we care about the guidance for the users. For example, we have a numerical example, which I will explain about in the next slide. Okay. And here's some important notion of what we call crypto stack. So we have a number of the projects in working group 2, and there are so many layers actually. So you can see here as a pyramid. The top layer, the implementations, the specifications, and the standards, protocols, multiple operations, primitives, assumptions. We cover our working group 2 standardization technology, cover most of them. So this is what we are proud of. And so like I promise, I give some example of the numerical examples. So why we do this, why we consider about this, because the implementation of cryptography is very difficult sometimes. So we can test. So if the people bring their, hey, this is a cryptographic algorithm inside, our product is very secure because this crypto is inside in the device. But we are not really sure that if the crypto implementation is correct or not. So we have to test if the implemented cipher is the intended one or not. So if you look at the standardization documentations, you can find the numerical examples in the annex, sometimes informative, sometimes normative. So what numerical examples are, also if you look at this annex of the numerical examples, you can find input and output of the cryptographic mechanisms specified in the documentations. And this is input and output are specified, like you can see in these tables. So this is really helpful if you like test your implementation is correct or not. Okay, so here we can take a look at what is the history about the working group 2 published standards. So how many years we have been working on crypto standards? In fact, we started this activity in 90s. With the next slides, I will explain a brief story of the working group 2, consisting of 3 generations. What about the first generation? Here are only 3 examples of our standard of the first generation, developed by the combinatorship by Louis and Marika. As for 9798 entity authentications, 11770 key management, 13888 non-repudiation. So this is what they are. As you may notice, the working group 2 standards typically consist of multiple parts. As you see here, both entity authentication and key management standards have 6 parts. But like if you are parents and you have kids, you would understand give a birth is not the end of the story, but you should take care of them, your children, until when they grow up. So is a crypto working group 2 standards. After some standard is published, you have to take care of by revising the standard. So here you see the working group 2 standards developed during the first generation. And you have 9797, 96 digital signature schemes giving a message recovery and check character systems, 14888, 10116 modes of operation for an L-bit block cipher algorithms, 10118 hash functions. So let me say a few words on 10118 hash functions because I like this. For instance, is one of the most widely deployed cryptographic mechanisms, but apparently SHA-1, which was developed in 90s and was broken in 20 years, after 20 years. And SHA-256 published in 2002, and then SHA-3 has been developed in 2012. We are now taking into account this trend. What about the second generation? Here you see the list of standards developed during the second generation. 15946 cryptographic techniques based on epic curves, 18014 time-stamping services, 977 authenticated encryption, and so on. But if you compare to other working groups in SC27, what makes us special is cryptography is based on mathematics. So we use mathematics a lot. But if you look at this view, you may be really surprised that a lot of formulas appear in the specification of the mechanisms. But we also take care of the users or implementators. So even if you do not have many knowledge of mathematics, there typically we are kind and we give the clear guidance how to implement the cryptographic algorithm mechanisms. So you should not afraid too much. Okay, there are some other working Bluetooth standards like blind digital signatures, anonymous digital signatures, anonymous entity authentication. So 18370 specifies blind digital signature mechanisms, which allow a recipient to obtain signatures without giving a signer any information about the actual message or resulting signatures. 20,008 specified anonymous digital signature mechanisms in which a verifier makes use of a group public key to verify a digital signature. 20,009 specifies anonymous entity authentication mechanisms in which a verifier makes use of group signature schemes to authenticate the entity with which it is communicating without knowing this entity is the identity, and which based on blind signatures and weak secrets. I would like to explain about the particular standards, the encryption standard 18033. And before that, I have to explain about the background, what happened to the world, global change. In the 90s, we began to enjoy the services that the internet enables, like internet parking. However, there has been major change advance in cryptanalysis. The encryption standard DES was broken. The attacks shown here that the time clock speed is much less than it should be. That was a very surprising result, even though the attack was theoretical, not really practical. As a consequence, there has been open competition to select the next generation block cipher to replace this. On the other hand, the guidelines cryptography policy was issued in 1997, saying standards and cryptographic methods should be developed at the national and international level. So encryption algorithms was out of scope in 1990 because the cryptography belongs to the military area. In early 90s, what was important is ISO IC 9979 procedures for the registration of the cryptographic algorithm. It contained 24 algorithms in 2001. In 2001, the project 18033 encryption algorithms was approved by JTC1. This is one of our main results developed within second generation. But if you want to encrypt your communication channels, you may want to use a symmetric ciphers, part 3 of 18033. However, the problem is that the senders and the receivers have to share the same key. To solve the problem, you can use asymmetric symmetric cipher that enables that deliver the key in a secure way. The project is very active, and it has now 5. It now has 6 parts, and one part is now under development, which is tweakable block ciphers. A few words on 18033 part 1. The biggest problem with ISO IC 18033-1 encryption algorithm is that how to keep good quality. If you want to standardize your cipher for encryption, you have to meet criteria. This is also important achievement from the second generation. Okay, here I explain about the ongoing working group 2 projects. So here is some overview of the working group 2 ongoing projects. You see the tables, the left most columns. This is working draft stage. This is the earliest stage, and afterwards we are the second stage called the CD stage, and then later stage is this stage or FD stage, and then you have international standards. Here in this talk, I will focus on these several standards you can see right up corner in this table. Okay, the first standardization technology I would like to explain is mode of operation for an n-bit block cipher 10116. The stage is done. This is amendment. This is amendment to the main body of the standards. This is the 4th edition, and abbreviation is like you already have 5 modes of operations like ECB, CBC, OFB, OFB, CTR, and now the new algorithm coming in this project. This is called the CTR ACPKM, a counter advanced cryptographic prolongation of a key material. So a little bit details of this mode of operations, what the properties are. To prevent the same plain text correspond to the same ciphertext by means of the use of the different SVs. And the use of the encryption operation of the cipher, you can use encryption for decryption as well. And it does not depend on plain text to generate the key stream. So you can do a pre-compute. It makes algorithm faster. Here is some reference. Okay, the next one is we have the second ongoing project. It is called the message authentication codes, MAX 9797, and part 2 mechanisms using dedicated hash function. The stage is this. This is already there are 4 MAC algorithms, which is HMAC and KMAC popular ones, and you have to use the hash functions as underlying mechanisms. You have many as many as 17 dedicated hash functions specified in ISO ITC JTC1. The first one, the RIPE-MD, and the third one is the famous SHA-1, and so on. And since that we had NIST SHA-3 competitions from 13 to 16, we have SHA-3 family algorithms. So this KMAC can be used to combining the SHA-3 hash function family. Okay, then the next one is okay. This is continued. So what is the KMAC? KCHAC message authentication code algorithms. What are the properties are? The SHA-3 family hash from 13 to 16 shall be used. And 2 variants, KMAC 128 and KMAC 256 can be specified. And both algorithm variants can support any security length up to 256 bits of security. And here's some reference. Okay. What about the nice thing about this standardization documentation is we have an informative annex in 9797-2. This annex discusses the security level, and it goes to assist the user, of course. And they consider documentation consider several attack strategy like forgery attack, key recovery attacks, guessing MAC, and so on. So it is really helpful. What is you if you want to know what kind of security this map can achieve, you can actually understand clearly. So the next example of the ongoing project is the key management 11770. So we have several. I would like to explain about this standardization project with respect to several parts, not only one part. So the first one is Amendment 2, Part 3, mechanisms using asymmetric techniques. The stage is DAM2 amendment. The new one is Key Agreement Mechanisms 15. It establishes a shared secret key to passes between two entities, and it describes of binary pairing-based key established mechanisms. And here are some by bibliography. Okay, the next one is the key management again. But Amendment 2, the Part 4 mechanisms based on weak secrets. So this document defines key establishment mechanisms based on weak secrets. That is, secrets that can be readily memorized by human, and hence secrets that will be chosen from a relatively small set of possibilities. It specified cryptographic techniques specifically designed to establish one or more secret key based on a weaker secret derived from a memorized password, while preventing offline brute force attacks associated with the weak secret. So annexes discusses again the selection of parameters. In this table, you can see which kind of categories they specify. Password authenticated key agreements and password authenticated key retrieval. And we have several 5 mechanisms for the first category. The second category, you have one mechanism, which is key retrieval mechanisms. So you have abbreviation and bibliography on your right. So this is a bibliography reference for 11770-4. So another project with respect to key management is this Part 5 group key management. In some applications, it is necessary for a secret key, cryptographic key to be shared by a group of entities. Moreover, in some cases, the exact membership of a group of the entities that share a key may change over time. This document is concerned with the techniques that enable a secret key to be shared by all members of defined groups with the assistance of a trusted third party known as a key distribution center. Provisions for adding and removing members of a group are also made. In this document, 2 types of key chains are considered. A forward key chain limits access to encrypted information in the future. That is a group forward secrecy, whereas backward key chain limits access to encrypted information in the past. That is group backward secrecy. Because the number of the keys in a forward and backward key chain is finite, the number of the key in the chain shall be carefully chosen at system implementation. So you have 2 mechanisms: key establishment with the individual rekeying, and key establishment with the batch rekeying for symmetric key-based key establishment mechanisms. So here are some references for this project. So the next one is again the key management. Part 7, cross-domain password-based authenticated key exchange. The stage is DIS. This document specified mechanisms for cross-domain password-based authenticated exchange, all of which are 4-party password-based authenticated exchange called the 4-PAIC protocols. Such protocols let 2 communicating entities establish a shared session key using just login password that there is a share with the respective domain authentication servers The authentication servers assumed to be part of the standard public key infrastructure, PKI, act as ephemeral certification authorities. They certify key materials that the users can subsequently use to exchange and agree on as a session key. So here are some, in this table you can see which kind of mechanisms is specified. We have 3 of them. Okay. So here are some references for this project. Okay, the next one is prime number generation, which is very mathematical elements. This is called FDIS. This document specifies methods for generation and testing prime numbers as required in cryptographic protocols and algorithms. Firstly, this document specifies methods for testing whether a given number is prime or not. The testing methods included in this document are divided in 2 groups. Probabilistic, the first one is probabilistic primary tests, which have a small error probability. All probability tests described here can declare a composite to be a prime. Deterministic methods is the second one. This is guaranteed to give the right verdict. These methods uses so-called primality certificates. Secondly, this document specifies a method to generate prime numbers. Again, both probabilistic and deterministic methods are presented. Here is this reference bibliography for this project. So we also have some topics for consideration, because we really watch what's going on in cryptographic communities, like what papers are presented recently, or the status of the security analysis or performance results. This result is sometimes we have to take into consideration. We have to discuss performance issues and security issues more importantly. So here are some topics in this table. You can see the topics for considerations at this meeting in September. The first one is 20008-3 mechanism using multiple public keys and so on. And if you want to revise standardization documentation, you have to propose like third item. And sometimes if for some certain types of cryptographic mechanisms, some people can find vulnerabilities, security weakness, then you can propose another mechanisms to achieve the required level of the security. So yeah, like the 8 items, inclusion of point-level standards, anonymous user signatures. So in these topics, the people would propose some new mechanisms to strengthen this standard. So I'd like to say a few words on future perspectives. The future focus of working group 2 activities will depend on market needs and, of course, technical seats. And we often regularly review the existing standards, because sometimes cryptographic mechanisms for some algorithms, people can find some weakness and people can attack. We have to consider maybe this algorithm has to be replaced, or maybe you can this development, this standardization documentation has to be strengthened by adding some new mechanisms with stronger security, and so on. And we also the security is most important issues, of course. So we often look for some information and gathering information from cryptographic communities by looking at recent state of the art of the technology in the literature. And also, what will be the very important for the working group 2 is a good relationship with industry. We also we often welcome industry members like companies, but they know the company people. They know that what will be the requirements for the cryptographic mechanism. They have to be fast cryptographic mechanism. They have to embed it on their devices. Could be has to be very fast or has to be very compact. So this is the industry needs. So the industry is very important partners. Okay, the conclusion for the first part. SC27 Working Group 2 has developed standards for through generations. The first generation in 90s, entity authentication and digital signatures, and under restriction of the standardization of encryption algorithms. The second generation is characterized by the 18033 development and others in advanced cryptography. And these algorithms are used in many standardization bodies like JDC1C17 and TC68 and so on. The third generation, they produce cryptographic standards of mechanisms and algorithms to meet diversified business needs for cybersecurity. So the Working Group 2 continues to work together with the other SDOs that enable more specific applications-oriented techniques. Okay, now I'm going to the second part. So this is a lightweight crypto. So here's some background. What would be the cyber physical systems, CPS? Cyber physical systems, CPS, connect information with a physical object like automotives, factory automations, and medical devices. And the security in these systems could be safety critical, which could impose an interesting challenge for cryptographers and also engineers. And in CPS, the problem is bringing the gap between publicly available scientific results and the real-world development. One of the key solutions is standardization by these activities. So here are some latest results. Actually, attacks. In 2012, if you look at the automotives, there is some communication available. Like if you have a key fob key and communicating with your cars. So this communication protocol was actually attacked. So this result is presented in ACNS 2012. So the securities that violates like location privacy, and even if the secure cipher like AES is inside, could be inside in this protocol, so this attack can be applicable. So using the secure block cipher primitive is not good enough. You have to consider all the stack like protocol, mode of operation, and primitives. So you have to consider all of them. So this is the lessons we learned from this paper. So you also you can find, if you look at the automotives, there are some another systems called the TPMS, tire pressure monitoring systems. The tire, you have 4 tires in a car. Each tire has some sensors, which is called the TPMS, capturing some informations, temperatures, tire pressures. So in the Usenex conferences, these systems can be attacked, so people can actually demonstrate that this attack. So what will be difficult for researchers or vendors to prevent this attack is you have to consider that the cost for the TPMS sensors. A TPMS sensor typically is very cheap. So typically 8-bit low-cost microcontroller is used, for TPMS sensors. So this means that the sensor has to be very cheap, and the cryptographic resources you can use for your implementations is very limited. So you have to be, your algorithms has to be very lightweight. So this is the difficult problem. So what is the lightweight cryptography? So the background is there is a growing demand for applications using smart devices, low-end microcontroller and RFID tags. It's very tiny devices, and that yet has some battery and communication abilities. So you have to make it secure. The security problems like confidentiality and data authentication and privacy, they have to consider. And the challenge for cryptographers or engineers is design cryptographic primitives or protocols that meeting system requirements. And to meet these requirements, lightweight crypto can be implemented under very restricted resources, such as low cost, low energy, and low power environments. So working group 2 already produced some results. Here are some list of publications and one under development project. We have part 1, general. You can find some criteria if you want to propose your cipher to this ISO standards. Your algorithm has to meet some criteria. Your cipher has to take some advantage over existing standardization standard ciphers. So you have to show what are the advantage over the existing standard, performance or security. The second part, or third part, symmetric ciphers, block cipher, stream cipher, and part 4 is the asymmetric ciphers. And part 5, part 6, hash functions, max, which I'd like to focus on the next slides. And part 7 is very new, and this is upper layer than primitives like protocol. This is broadcast authentication protocols. And the new development is going on, authenticated encryption. So the first technology I'd like to focus on is hash function standards 29192-5, which is published in 2016, 4 years ago. You have 3 algorithms, one of which is software-oriented. It's called Alexander W, 256-bit hash functions, which are optimized for 8-bit microcontrollers. And two of these are called Spongent and Photon, which is both of which are hardware-oriented hash functions. So you have to, if you want hash functions very compact in the hardware, you can use either Spongent or Photon. So I'd like to explain about why hash functions are important. Because hash functions is very important because they are used in a wide variety of cryptographic applications like digital signature schemes, key derivation functions, random bit generators, and they can achieve security in these cryptographic applications. And the hash functions are standardized in ISO and NIST, and they are needed in any cryptographic software library, mostly, for randomness extraction and public key encryption. Hash functions are important, but we also face the crisis with respect to hash functions. And to solve this crisis, NIST has launched a Sharding competition. What is the crisis? In 2005, there are some very strong results, breaks of famous hash functions, MD5, SHA-1. In 2006, federal agency announces the users should stop using SHA-1 for certain applications, and the users must use the SHA-2 family for them after 2010. And the NIST recommends the transition from SHA-1 and 2. But researchers concerned that SHA-2 may be vulnerable to similar techniques that was used to attack SHA-1. because there are some similarities in the design principle between SHA-2 and SHA-1. And so in 2007, NIST started the SHA-3 competition. But what was behind the attacks? There was some breakthrough. Professor Wang, Chinese researchers, developed some novel method to attack SHA families, which is called differential cohesion search. So attack complexities actually can be optimized by using the fact there is no secret key information in the hash function specification itself. So she can use this fact. So what's going on in the SHA-3 competition? The first round, there were 51 candidates, and this is down to the 5 finalists. And finally, 2012, NIST selected Kechak as a winning algorithms in October 2012. So I would like to explain about the basics. What is a hash function? So very simple. It maps input strings of the arbitrary length to short output strength of the fixed length. N-bit hash function returns on hash function returns an n-bit hash value. And like I said, the description of the hash function must be publicly known. A hash function does not require any secret information for its operation. Like it can be used like a fingerprint for a human. What are the hash function properties? You have several properties that should be expected in cryptographic applications. The first one is a security property, of course. The pre-image resistance, it has to be difficult if you are given output. It must be difficult for you to find the input that is mapped to the given output, and so on. But it's very difficult to achieve for the designers to achieve the collision resistance. The attacker can freely choose a pair of the inputs that maps to the same outputs. This is collision. So the finding collision must be difficult, computationally difficult, but this property is very difficult for designers to achieve. And the second property is performance, of course. Like every symmetric key algorithms, hash functions has to be efficient. It runs fast on the CPUs, and it has to be compact in hardware and software, and so on. So I'd like to move on to the explanation about the lightweight cryptographic hash functions called LW, which I was involved as a core designer. So the design goal is it should be compact and fast, optimized for lightweight applications in a wide variety of environments. And most importantly, our primary target CPU is our 8-bit. So we can implement on a very cheap device. Because the low-cost 8-bit CPUs are very popular at the time. Over 4 billion 8-bit controllers were sold in 2006. And you can find several microcontrollers which has very limited resources, as you can see in this table. Sometimes RAM size is lower than 256 bytes. So yet, result should achieve the 120 security level. This is considered to be very high security. And we'd like to provide proofs reducing the security of the result W to that of the underlying block cipher performance. So when we started designing lightweight hash functions, the W, the problem was, like you see here, how you reduce the memory requirements. So this is the picture shows the conventional, the hardware implementation of the conventional lightweight hash is called MAME. But you can see here feed-forward registers. That this is too big. So we'd like to replace these feed-forward registers by considering some novel by developing novel mode of operations. In the end, what we came up with is, as you can see here, LW1 mode. So this mode can be proved to a collision resistance if the underlying block cipher behaves as a pseudo-random function. So this mode does not have the feed-forward inputs. So this was the problem with the conventional lightweight hash functions. So this contributes to a small memory requirements. This is very nice. So this figure in the middle is the structure of the result LW. So what about the underlying block cipher for this function? So this should be compact in software and hardware, and to offer reasonable speed and hardware, both high-end and low-end CPUs. And the algorithms look like this. You can see here in the bottom. So since the SHA-1 hash function was broken, so we are really we were really careful about the security. We evaluate hash functions with respect to all relevant attacks, like differential attack, linear attacks. Most of the attacks are relevant to the block ciphers, not really relevant to the hash functions, but nevertheless, we care about all of the major block cipher attacks. And then we confirm the security of the underlying block cipher of the result LW. So what about the performance? This is the reason why the result LW exists. So result LW is efficient, more efficient than SHA-256 on certain environments, certain platform. As you can see here, it requires result LW requires only 50 bytes RAM, which is very nice, while achieving 3,478 cycles per byte. For short messages, this means 84% smaller than SHA-256, while running 20% faster. So this is not the end of the story. We after publishing result LW papers, and we standardized result LW specified into lightweight cryptography standard in ISO. Our next challenge is how we apply this result LW hash function to TPMS security. So we came up with some novel mode, as you can see here, up. So we convert result LW to multiple independent PRF random functions in TPMS. Like in the car, you have the 4 tires. You can obtain 4 independent PRF by adding some a little overhead. So we presented these results in some famous conference regarding car security called SCAR Asia. So let me explain about the another CPS, another lightweight cryptography related requirements, which is called real-time requirements. So you can see here in the figure, there is some factory. In the factory, there are many devices communicating each other, but the resources are also limited. And also requirement is quite severe. It is called real-time requirements. AES counter modes can be problematic. This is a problem for programmable logical controller called PLC, because cryptography eats too much resources on PLC. So this is what the people don't want. And also for automotives, real-time requirements is very important. So if you got a V2X system, over-the-air programming OTA gets a lot of attention these days. And ITUT's SC27 is developing a protocol for remote software update. The hash, MAC, and PRF play key roles in this protocol. But if you look at the in-vehicle system, if you've got inside of the car, a short message performance is quite important. The packets can be as short as 8 bytes. It's very short. If you got the CAN protocols to 64 bytes CAN-free protocols. As I repeated, real-time requirement is very, very severe. From 1 millisecond till 100 millisecond. periodic tasks must be processed. So if you want to implement your cipher in your devices, so your implementation has to be very efficient or compact. And there are 50 to 100 ECUs employed in the car. So limited cost can be paid for each ECU. And the cost comes from the circuit size is embedded in the hardware and the ROM or LOM size in the software. So I would like to present some nice lightweight cryptography mechanisms that can meet these real-time requirements, which is called SC27 specified in 29192-6 lightweight MAC standards. This is very recent standard, last year published. Three mechanisms, this SC and light MAC mode and SUDIC mode. The second one is the mechanism is used at the mode of operation layer, so upper than primitive layer. So, and the SUDIC mode is it can be used for less than double hash function, just as explained. And this is faster than standard normal method, HMAC SHA-256. And SC27 has some very nice implementation results that can achieve the speed of 7 cycles per byte on ARM Cortex-M4. So comparing the AES-120 SCMAC, SC achieves 12 times higher speed, and yet program size is the first to 20. So there are some collaboration work of ISOYC SC27 Working Group 2. This is collaboration work with ITUT SG17. This standard X.1362 published in 19 June, 3 years ago, the first ITUT IoT security standard. So what is SC17? This is standardization organization regarding telecommunication security. And the scope is reduce the overhead by encrypting the only data that are sensitive. Very simple, but can be very effective. The main contents, as you can see here, are the specification of how to communicate cryptographic communications mechanisms called EAMD, encryption with associated mask data. And there are some user guidance, which ISOYC SC27 WG2 provided as an expert. But normally SG17, the expert on cryptography is limited. Very small number of them are cryptographers, but most of them are not cryptographers. So we have to help them. So how the EAMD root protocol looks like? What is the idea? The idea behind this protocol is, as you can see here at the left side, it can reduce the overhead by encrypting the only data that are sensitive. This red part, the data field indicated in the red part, in red, is actually the sensitive. So the encryption algorithms should be applied to this red part. And the white part, on the other hand, so this data field does not contain sensitive data. So the algorithms, cryptographic algorithms, should not be applied to this white data field. So this is very simple, but the overhead is you have to tell which data field is sensitive or not. So you have to have some extra data, but this data can be very short of 100 bits or something. And using this idea, you can construct some protocols. I can see on the right side. This is trivial, so this is a natural way of using it. But because of by using these protocols, you can, in some situations, you can meet these real-time requirements at the protocol level. There is another trend on a lightweight crypto. NIST holds several workshops in the past regarding lightweight, And also NIST started some lightweight cryptography standardization projects. And the timeline is from now, they are now in the second round stage, and probably 8 finalists should be selected to advance round 3. And selected, they will select winners in 2012, selection for the second round is security or maturity are considered, but performance was not considered. The main issue with the first round candidates include domain separation, message and tags. How to separate this can be sometimes causes a problem. Now you can find some results of the first round in some reports that NIST has already published. You can find the link. And the discussion is now how many winners can be selected. Some people said that the winner could be multiple, and the categories could be considered in NIST. So here is the conclusion for the second part, lightweight crypto. The problem is the bringing the gap between the publicly available results and the real-world development. Standardization bodies like ISO SC27 WG2, NIST, ITUT are quite active to solve this. The requirements-oriented view and the use of lightweight crypto could be the key solution to them. Lightweight crypto for the size requirements, I presented Alexander W requiring some small RAM requirements. And its applications presented in some car security conference. Lightweight crypto regarding real-time requirements. I presented some ITUT X.1362 EAMD protocols with the help of this protocol is developed with the help of SC27 Working Group 2. And I presented also cryptographic algorithms, lightweight MAC, meeting real-time requirements specified in lightweight crypto-6, particularly SASQ12. This is software-oriented, very fast on ARM. Okay, so this is it. Thank you very much for your attention.